So these scores that you see on the screen are the tests that I have corrected from my B days. So I still need to correct some from my A days, obviously, but I'm almost done, and they're doing about as well as you guys did. So first of all, this one went way better, I feel like, than a lot of the other tests. You can see how many people were like 80s or above. So if you're in this area, you need to seriously consider and evaluate what you are doing to be in the bottom 4. Because at this point, it's not just that the class is hard and it's too much, because there are this many people that are being successful and have figured it out. So if you're down here, you need to seriously evaluate what's happening, especially considering that they're ordering tests this week. They're ordering tests on Friday. If you don't change what you're doing and you're in this area, the chances that you're going to pass the exam are very low. You have to ramp it up at this point. So, just take that into consideration. I support you no matter what, but looking at these scores, it does concern me if you're on the lower end than the higher end. In the past, scores were a little bit lower, so if your score was low, it wasn't a huge concern, but now we're getting to the point where if you're down here in the 50s or 30s or 20s, I would really think about between now and Friday whether or not you're going to take the exam. Because remember, once they order the exam, they won't take the fee off your account. And I think it's $95 or something like that. So overall, the exam I feel like went really well. I'm not going to talk about it this class period. I'm going to talk about it next class period because some people still need to take it. The one thing that I'll mention before we start on the new stuff is I built into the exam some questions to help raise your grade. So if you look at the exam, there's 12 multiple choice, but it was still out of 50. So you could miss up to 2 in the multiple choice and still get 100%. Same with the free response. I tried to build in some questions so that you could earn points back if you missed some on the calculating or creating the confidence interval. So even if you had 100, make sure that you go through and see if you missed any, because you may have missed one of the multiple choice even though you have 100. I will go over number 11. So if you didn't get number 11 right, I plan to go over that one in class. And there's a free response that I might talk about, but other than that, things went really well, and I don't think very many of you need to do test corrections. So there's that. Okay, so this is Unit 6 stuff. So I brought you your Unit 7 stuff, and it's, we're going to do Unit 7 slightly different because we're in the home stretch now. We're getting very close to your actual AP exam. And I want to make sure that we get in hypothesis testing and sampling. So Unit 7 and Unit 8 before you test. So if you look at your calendar, it's set up differently. And the packet that I brought you, this is your notes and your can you do's. So this is all of the work for Unit 7 besides the overview and the test. And the test will be a take-home test. It will not be an in-class test. So the reason why I'm doing this is because I want to be able to do some of the easier lessons at home for your homework. So today it says that we're doing 70 in class and that you're supposed to do 71 at home. Well, I was able to make it through both in second period. So we'll do both of these lessons in class, and then the only homework that you'll end up having is these 3 problems on page 705 and these 2 problems on page 707. And I'll tell you that again at the end, but as far as this is set up, like when we're supposed to do power of a test, we should do that whole lesson and practice questions in class so that you only have this to do at home. So I don't want you to think you're going to have a lesson and a homework assignment and a lesson. These should all be done within like 1.5 hour chunks. So I think that'll be clearer as we move through, but I did want to highlight that that things are set up a little bit differently, and your can you do's are very short. They're like 3 to 5 questions instead of pages long. So that's our plan for Unit 7. I may have to adjust some stuff because I'm not sure that I want to do lesson 75, distance learning. And I had the wrong calendar. So Wednesday the 24th is also distance learning. So I needed to make that gray for myself so that I knew that it was distance learning. So when I adjust, if I adjust, I'll just make sure to give you guys a revised calendar so you know exactly what's happening. This day's distance learning. Okay, was that all of our housekeeping stuff? Yes, so you got your divider, your tab, all of your Unit 7 stuff, and your calendar. Oh no. Crushed Minnie and Mickey. Okay, so we will get going on significance tests. Both of these lessons are pretty short, and the first one, this lesson 70, is basically a review of something that we've been talking about since the first week of class. So, sampling distributions, Unit 5, I think is arguably the hardest unit in this class. And then what comes after that is confidence intervals, and you need the idea of a sampling distribution to be successful at that. And now we build on that significance test. So Unit 6 and 7 are highly related to sampling distributions, which was Unit 5. So I'm hoping that as we have moved through these lessons, you're feeling more confident about the idea of a sampling distribution. And it seems like based off of your test scores, you're feeling pretty confident on confidence intervals. So that's where we start this unit. We're coming out of sampling distribution and confidence intervals. So this blank is confidence intervals. Confidence intervals are one of the most important types of statistical inference. I'm going to highlight that word inference because that's what these 3 units are on. They are on inference. We are looking at a population and we are trying to get information about that population or infer things about the population based off of a sample. So in a confidence interval, your goal is to estimate a population parameter. So for last unit, we were trying to estimate mu or p. We were trying to estimate the proportion of something or the average of something. The second most common type of inference, so the first most common is confidence intervals. The second type of inference is called significance testing. This has a different goal than a confidence interval. So the goal for significance testing is to assess the evidence provided by data. about the parameter. So this idea, this assessing the data or assessing the evidence provided by the data, is something that we've been talking about all year in anticipation of this lesson. So the one that I remember the most is the Ford Focus example, where I told you guys there's this guy that claims that his Ford Focus gets 41 miles per hour. That seems really high. So do we believe him based off of all this information we gathered about other Ford Focuses? This whole chapter is around that idea of a claim, somebody making a claim, and us getting data to test the claim. So we are going to look at this idea around an example of a basketball player. So we have a basketball player that claims to make 80% of the free throws that he attempts. So if he shoots 10 times, he makes 8 of them. We think that he might be exaggerating. So to test this claim, we ask him to shoot some free throws. Well, we're going to do this virtually using an app that's provided by our textbook. So this is the picture of us having this basketball player shoot. At the top it says shots and it has a 25. This is actually 50. So I would change that number of shots that he made to 50. So what's happening in this picture is it's showing the percent of baskets that he makes. So this very first part where this graph starts, this is showing that he made the first basket that he shot. And then it goes down here because he missed the second one. So what this is showing is that when he only shoots a few baskets, his graph is all over the place. But as he shoots more baskets, the percent that he makes starts to even out. So in the beginning, it's crazy. It's like he makes the shot, misses, makes misses, makes misses. But as he approaches like 50 shots, this starts to even out around 64%. How do I know that? Because I'm like comparing it to the y-axis. Like the line starts to get straight around 64%. So the parameter of interest in this example is the proportion P of free throws that the player will make, and our simulation sets that up as if he shoots forever. So the long run percentage that he makes is 80%. In the long run, that's what they mean by forever. In the long run, his average will even out to 80. In the short term, it's bouncing around, but as you do more and more shots, it evens out. Our player claims that he's an 80% shooter. So I'm going to highlight that. Our player claims that he shoots 80%. So to test his claim, we're going to let the applet simulate, change that to 50 shots. So if he only makes 40%, so this is not what's happening in this picture. They're just saying he claims to make 80. If we had him make some shots and he only makes 40% of them, we have fairly strong evidence that he really is not an 80% shooter. So this is saying in some cases, our sample might be obviously too low. Like if he really only shoots 40%, we would get that value and go, I'm pretty sure he's lying. But what happens when it's not that low? What happens when it's not obvious that he doesn't shoot at that percent? So that's what this is saying. What if he makes 76% of his free throws? Does this provide evidence that he's not telling the truth? So if he makes 76%, this provides some evidence that his true long-term percent may be less than 80, but it's not nearly as convincing as if we would have gotten a sample value of 40%. So if all we do is look at sample data, it can be hard to determine if a claim is true. So in this case, he shoots 40%. It's easier to use the sample data to say, I don't think that claim is true. But in this case, where he's at 76%, that's hardly any evidence that he's not telling the truth. So what statistical testing does, or what a significance test does, is it weighs the evidence against a claim. It's a mathematical process for weighing the evidence against a claim. So instead of just looking at the sample data and saying, oh, that sample looks really low, we can actually calculate a statistical test to determine if it gives evidence against the claim. So it's showing you the language that you use for a claim and a counterclaim. So this guy is saying the claim is that the true proportion is 80%, and underneath it explicitly says what that is. The player really makes 80%. The counterclaim is that the player really makes less than 80%. And we have this counterclaim because our sample gave us a value that was less than 80%. So this formalizes what we're saying above with our basketball example. A significance test is a formal procedure for using observed data, to decide between two competing claims. These are also called hypotheses. That's why your divider says hypothesis testing, because this is also testing hypotheses. So our competing claims are the makes 80, makes less than 80. The claims are often statements about a parameter, and remember, our most common parameters are P, like in this example, or mu, like in the example we're about to discuss. So we are now going to talk about a statistical test to see which claim we think is true. So on the next page, we learn how to state our hypotheses, because the first part of any significance test is clearly stating your claim and your counterclaim. So a significance test starts with a careful statement of the claims we want to compare. In our free throw shooter example, the player claims that his long run proportion of made free throws is P equals 0.80. This is the claim that we seek evidence against. So we're not doing this test to show that the claim is true. We're doing the test to see if there's evidence against the claim. We call this P equals 0.80 the null hypothesis. So NULL. Its notation is capital H sub O. It's got a little O there. And lots of the time that gets abbreviated down to the HO. H-O, the HO. The claim that we suspect to be true instead of the null hypothesis is called the alternative hypothesis. We abbreviate that as capital H-A. We don't ever call that HA, we say H-A. Sometimes we say H-O, but most people say HO. So in this case, our alternative hypothesis is that we believe the player might be exaggerating. We believe our player might be exaggerating. So our alternative is HA is that P is less than 80. So a couple of things to note before we try this on our own. The null, HO, is always an equal. The claim, the null hypothesis, is always a statement that has an equal sign. So every null hypothesis has an equal sign. HA will always be an inequality. So HA is always, our inequalities are greater than, less than, or not equal to. The problem will give us an indication of which one we should choose. So in this case, we chose the less than because our sample value was less than. So HO is always an equal sign. HA is always an inequality, one of these three things. So now let's look at that compared to this problem, the Hawaii problem. So the Hawaii Pineapple Company, at the Hawaii Pineapple Company, managers are interested in the size of the pineapple grown in the company's fields. Because most of the time when you buy fruit, it's weighed and they get paid based off of the weight. Last year, the mean weight of the pineapples harvested from one field was 31 ounces. So I'm going to highlight that. Last year, our pineapples weighed 31 ounces. A different irrigation system was installed for this growing season. So after these pineapples were harvested, they installed a new irrigation system, and the managers wonder how this will change the mean weight of the pineapples. So I'm going to highlight this. The managers are wondering how this change affects the mean weight of the pineapples. So they want us to state the appropriate hypotheses and define the parameter of interest. So HO, our null hypothesis, would be what we got last year. Our old system allowed us to grow pineapples that were on average 31 ounces. This is a big number. So one, it's not a small number like a percent. And two, in the problem they're telling us we're looking at a mean. So instead of having a P, this time we have mu is equal to 31 ounces. So the null is the average weight we're used to getting. The alternative will be an inequality, and we need to figure out which one. So this says the managers are wondering how it's affected. So they're not making a statement like the managers are wondering if the pineapples weigh more, or the managers are wondering if the pineapples weigh less. The managers are investigating if the pineapples are different. So how we express that is mu is not equal to 31. Because we don't know what effect the irrigation system will have. The new irrigation system might be awesome and our pineapples will weigh more, or it might not be awesome and our pineapples will weigh less. So this is an example of a two-sided hypothesis test. So that's this box here. The second bullet point says a alternative hypothesis is two-sided if it states that the parameter is different from the null hypothesis. So we're not sure if it's greater and we're not sure if it's less. We're just wondering if it's different. That's called two-sided because it could be more or less. A one-sided hypothesis test is if it states a parameter is greater than or less than the null. So we have an example of each above. And I'm going to write that in. So this guy, this first one about the basketball player, he's a one-sided hypothesis test. It's one-sided because we think that the true value might be less than. This guy is a two-sided hypothesis test, and it's two-sided because we are wondering if it's different than 31. So these inequalities would be a one-sided, this inequality would be two-sided. So the other part of this example that we need to do is state the parameter of interest. So we say our null is that it's 31. Our alternative is that it's not 31. What I mean by it is what we have to define. So we say where, and I'm just going to write it to the side of my two hypotheses, where mu is the mean weight of pineapples grown in the field this year. So we state our hypotheses and then we define the parameter. Okay, so let's do another one. So for each of these, we're doing this exact thing. We're going to say HOHA and then define our parameter. So according to the website, sleepdeprivation.com, 85% of teens are getting less than 8 hours of sleep. Janie wonders whether this result holds in her large high school. She asks an SRS of 100 students at school how much sleep they get on a typical night, and 75 of them responded that it's less than 8 hours. So I like to do this example together because it's a little bit more challenging identifying what our parameter is. In this case, our parameter is a proportion. So 85% of teens this is P. The claim of this website is that 85% of teens get less than 8 hours of sleep. Janie takes a sample and gets a P hat of 75 out of 100 who get less than 8 hours of sleep. So our parameter of interest is the proportion of students, not the hours of sleep. Well, our sample is 75%. So we base our hypotheses off of this. The null hypothesis is that teens get, 85% of teens get less than 8 hours of sleep. So equal sign. The proportion is truly 85%. Our alternative is based off of the sample. So we get a sample value that is less than the null. So our alternative is that P is less than 0.85. Notice that in both of these, you use the claimed value. Both of those are 85%. What you use the 75% for is to decide what symbol do you put in the alternative hypothesis. So you use P hat to decide what symbol you're using on your HA. So this is our claimed, always. We use sample if they give us that information to decide the alternative. Then the last thing we have to do is say what P is. So we're testing the claim that P is 85% against the claim that P is less than that, where P is the proportion of teens who get less than 8 hours of sleep. So we state our null and alternative, define the parameter. Okay, to give you some practice, you try the Census Bureau question without me and all unfreeze so that we can check our answers against each other. So you try the census question, number 2. So about 45 more seconds. About 10. Okay, I got that the null is 10 minutes. Mu is 10 minutes. Our alternative is that it's longer than that, so greater than 10. So let me give you some help on how I knew these numbers. So first of all, I knew that it was mu because they're saying, not that one. I knew that it was mu because 10 minutes is a bigger number. It's not a percent, and they didn't give me a percent anywhere in the problem. We can't use this word average to tell us that because that's not what this problem is about. This problem is about the time that it takes to complete the form, not the average household. And then I knew that the symbol would be greater than because it says we suspect that the actual time may be longer. So I got the greater than from what I highlighted in green. Then I define my variable as the time it takes to complete the census form for the average household. So the census is where they ask you how many people live in your actual house. So for the average household that's smaller, it's probably around 10 minutes. A household that's not average is if you have like more than 5 people living in your house. Do you guys want to try one more before we move on? Or do you feel okay? Okay, I think we feel okay.